Alright, so today I'm gonna be talking about another approach for name entity recognition. Here is the title of this article is a comparative study of pre-trained encoders for low resource name entity recognition. Because in practice everything is all labeling is expensive, and so we are in the world of low resource. That's why we need to work on, for example, few-shot learning, zero-shot learning to tackle this problem, or transfer learning and many different ideas. Pre-trained language models are effective components of few-shot name entity recognition. When augmented with continued pre-training and task-specific out-of-domain data, or fine-tuning on in-domain data. However, their performance in low-resource scenarios where such data is not available remains an open question. So they introduce in that article an encoder evaluation framework and use it to systematically compare the performance of state-of-the-art pre-trained representations on the task of low-resource NER. Then they analyze a wide range of encoders pre-trained with different strategies, model architectures, intermediate task fine-tuning, and contrastive learning. The dataset is, for example, here is Connell 2003 for English, and this one is also very popular, this dataset, on 2 nodes. And also few-NER, if you want to work on few-shot learning for name entity recognition, this is very nice. And so this is few-NER. So you see a lot of entities, but very few examples for each of them. And there are other datasets as well, such as Wikigold. So for example, Wikigold has these entities, these gold entities. But how well do representations learned by different pre-trained models encode information that benefits these low-resource scenarios? What can be observed for different categories of encoders, such as encoders trained with masked language modeling versus encoders that are additionally fine-tuned on downstream tasks or optimized with contrastive learning? How do they perform across different datasets and languages? So we have one encoder. We have encoder, you can implement it differently, and we have a readout that we can implement differently. So this encoder readout that we say, this framework, so for each of the N classes, we have different classes such as person, location, and organization. We randomly sample case support tokens. For example, here we have 2 support samples for class person. And the encoder provides an embedding for each token, and the readout model G assigns a class to a query by comparing its representation Q sub J that comes here to the representation, each of these representations Z6, Z5, because these are representations. For example, if you are working with Protonet, you can have different representation, and this is your query. Your query should be as close as possible to one of these prototypes. And NER is typically formulated as a sequenced labeling problem where the input is a sequence of tokens and the output is a corresponding T-length sequence of entity. In contrast, few-shot learning is cast as an episodic NVK shot problem where in each episode n classes are sampled with k examples, each to construct a support set. And of course, we have a query set. We may have more than one query. So in a sequence labeling problem like NER, samples are typically sentences due to importance of contextual information for token classification, but care has to be taken to ensure that the sample sentences domain contain no other entities. In particular, there should be no entity overlap between the support and the query sets. So our framework consists of two modules, an encoder and a readout module. As shown, the encoder provides an embedding of token X. So we have a word, we have a token X, and we want to embed it. And the readout module is responsible for assigning class to each token. But in different papers, we use span prediction. So instead of a word, we are working on a span. So our span may be more than one word. That is more general. Depending on the readout approach, the sys class is represented either by its prototype embedding or by its associated set of token embeddings for nearest neighbor classification. And the decision is made by comparing the embeddings with each of the n-class prototypes built from the support set, or with each of the token level embeddings. So you have seen that for any for example, here we have it's just a linear classification that can be extended to multinomial logistic regression to deal with n-way or multi-class setting. So the probability that this token X prime belong to class C, this class C, for example, class person or organization, the probability is here. This is the score and this is normalized. And this W is a matrix of n rows learned from support set. And WI is just the ith row. This is the ith row of the matrix W. But here in the nearest neighbor centra is more accurate because we are minimizing with the central of all embeddings. And of course, some paper, instead of just doing an average over them, they use cross attention, which I've seen in some papers, that instead of just this average, simple average, they use cross attention too, because not all samples are the same. You can attend to different samples more than the other, so it's a distribution of your attention. But in the first article of Protonet in 2017, they just use this approach because it's very simple. You just take the average and you don't discriminate between different samples. You treat all of them the same. And for pre-trained language model, these models are pre-trained on a large general corpus in self-supervised manner without any task specific. And we consider 6 representative for views: BERT case, uncased, case and uncased, span BERT, XLNet, Albert, Roberta, deep sets BERT and got BERT, and XLM Roberta. And so recent research has shown that intermediate task training can build in significant performance gains on target tasks, even in low resource setting. Because some people argue that in low resource setting, it's not good. First of all, they argue that you are in an anisotropic model, it is collapsed into certain dimensions, so it's not justifiable. But even in low resource settings, practically experiments has shown that you can do it. So we evaluate 3 BERT encoders that are fine-tuned on token level, sentence level, and document level intermediate tasks. And we also experiment with BERT Connell and a BERT model fine-tuned on this dataset. It is fine-tuned specifically on this dataset for name entity recognition. And we can combine this pre-trained language model with contrastive learning. And your contrastive loss is just the difference between your embeddings of each sample and the main, if they have the same label.